Hi, I'm Shanawaz. In last lecture we were discussing the homotopy. Let us recall the definition of homotopy. Suppose we have two topological spaces X and Y, and suppose we have two continuous maps, say F and G from X to Y. Then we say that these two maps F and G are homotopic, denoted by F is homotopic to G if their X a map, suppose H from X cross the unit interval 0 1 to Y such that when we restrict H to 0, we get this little f, and when we restrict H to 1, we get this little g. So in that case, F and G, they are homotopic. Note that this H is actually a family of continuous maps for different values, say for different values of t, where t is a value from this interval. For example, let us take the topological space X to be the set of general linear matrices and Y be another topological space of general linear matrices of order 2n. Note that this G, L and R, set of all n cross n matrices which are invertible, this is identified as the topological space R to the power n cross n. Note that this is a topological space with usual topology, and G, L and R is nothing but R to the power n cross n. So, and the topology on this G, L and R is the intuitive topology on R to the power n cross n. So let us define maps F. So we have, let F and G be the maps from G, L and R cross G, L and R to G, L 2 and R, where F takes the pair A, B, where A and B are n cross n matrices to the matrix. Note that A and B are square matrices of order n, so F has to map this pair to a square matrix of order 2n. So we can define F like this: a block matrix like this with the leading blocks A and B, and here A is n cross n matrix, B is n cross n matrix. So this is a matrix of order 2n, and G takes this pair AB to AB 0 0 and I. Here AB is n cross n matrix, I is n cross n matrix, identity matrix. So this is the matrix of order 2n. Now what we had to show, we need to prove, we need to show F is homotopic to G. So we have to cook up a homotopy, say H, which will show that F and G are homotopic. Now let us define a homotopy like this. Define define h. Here this is over x and this is over y. Define h from x times the interval 0 1 to y. Here this x is glnr times glnr and y is gl 2nr. This is same as glnr times glnr and this y is gl 2nr. We'll define this homotopy like this. Now by h of an element here, that is a pair a b, and let us pick t here. So this is mapped to a 0 0 I. Here a is n cross n matrix, I is n cross n identity matrix. So this is a matrix of order 2 n. Then cos of t sin t minus sin t cos t. Then I 0 0 b, and finally cos t minus sin t and cos t. Here we take t from 0 to pi by 2, where 0 is less or equal to t is less or equal to pi by 2. Actually t has to be t must belong to interval 0 1. Now what we do, so if we plug we can rescale this to make it from 0 to 1. Say you put capital T from 0 to 1 and then you appropriately multiply by 2 by pi, and then you can plug in and you will get 0 to 1 scale. Let us keep capital T here. Where T is 2 by pi times T. So if we substitute T, if we replace this T by this capital T, we will get 0 to 1 scale. Note that this H is a continuous map for each value of T, because these are matrices and hence these are linear transformations and hence continuous. Now what we had to prove, when we restrict T to 0, what do we get? H of AB 0 will be equal A 0 0 I times 1 0 0 1. Actually this is identity matrix over here, and this is I 0 0 B, and finally 1 0 0 1 here. So when we solve this, we get a 0 0 b. So this is nothing but f of ab, and that is when we restrict h to 0, we get f. Similarly, when we restrict this h to 1, I mean pi by 2, sorry 1, so we'll get over here a 0 0 I 0 1 minus 1 0 and then I 0 0 b, and finally 0 minus 1 1 0. Now this is same as when we multiply these two matrices. This is 0 times first column and minus times second column, so this is 0 minus I. Now 1 times first column and 0 times second column, that is first column. Now let us evaluate this. 0 times first column, 1 times second column, so this is 0 b, and minus 1 times first column, 0 times second column, that is minus I 0. Now on multiplying these two matrices, this is 0 times first column, this is 0 times a, and this is ab here, then 0 times I, a times 0, that is 0, that is then minus times 0, and 0 times b, that is 0, then minus I times minus I, that is I, and 0 times 0 is 0. So that is g of ab. Hence when we restrict h to this to 1, we get g. Hence these two maps are homotopic. Now next we will prove that we'll prove a proposition which states that composition of homotopic maps are homotopic. Composition of homotopic maps are homotopic. That is, if f is homotopic to f prime and g is homotopic to g prime, where f and f prime are continuous maps from topological space, say x to y, and g and g prime are continuous maps from topological space, say y to z, then g composed with f is homotopic to g prime composed with f prime. Proof. Suppose we are given that f is homotopic to f prime and g is homotopic to g prime, so there must exist homotopies. Suppose f is homotopic to f prime, where the homotopy say f. So f will be a map then from x cross 0 1 to y, and g be homotopy to g via the homotopy say capital G from y times the unit interval 0 1 to z. Therefore when we restrict f, to say 0, we get little f, and when we restrict f to 1, we get f prime. This is for all x in x. Similarly, when we restrict g to 0, we get g, and when we restrict g to 1, we get g prime. This is again true for all y in y. Now we'll cook up a homotopy. We will cook up a homotopy, say h from x times the unit interval 0 1 to z. Actually we have here, it is x, then y, then z. So here we have f and f prime, and g prime. So a map from x to z will be g composite with f, and again a map from x to z, the map from x to z, that is g prime composite with f prime. Note that these are both continuous, since f prime g prime are all continuous. So we have to prove this composition map g composite with f is homotopic to g prime composite with f prime. So now we have to exhibit this homotopy. We have to show how this homotopy is gonna look like. So let us define so we need to cook up this homotopy such that when we restrict this h to 0, so this must be equal to g composite with f, and when we restrict this to 1, we must get g prime composite with f prime. So this has to be true for all x in x. So define this h, which is from x times the unit interval 0 1 to z, as, so what we do, we take this pair xt, and this x is from x and this t is from this interval 0 1. So we define this to be the homotopy G with first with first component f of xt and second component t. Note that this homotopy is well defined. One can see that this f of xt, this belongs to y because f is a homotopy from x to y. So f has to be f of xt has to be in y. Therefore this f of xt and t, so it's a pair. This is in x and this is in interval 0 1. So this belongs to x times the interval 0 1, and hence when we take G of f of xt and t, so this is a pair from x. This pair belongs to x cross 0 1. So when we operate G onto this pair, this must belong to z. This belongs to z, but this is same as h of xt. So this is well defined. Now let us see what will happen when we restrict h to 0. So this will be equal to G of f of x0 and 0. This is same as G of, when we restrict f to 0, we get little f. We get little f. Say this is f of, sorry, this is f of x and this is 0. Now when we restrict G to 0, we get little g. So this is G of this element over here. So this is G of f of x. So this is same as G O f. Actually this is G of f of x by definition of h. So this is G of f. Similarly, h restricted to 1 is same as G of f of x1 1. This is same as G of now when we restrict f to 1, we get f prime, and finally when we restrict G to 1, we get G prime. So this is G prime of f prime of x. So this is same as G prime of f prime. So this shows that this homotopy S shows that G composite with f is homotopic to G prime composite with f prime. Hence G composite with f is homotopic to G prime composite with f prime. So this is pretty much of it. Now let us move to other definition, which is homotopy equivalence. So we have definition. Let us consider two topological spaces x and y. Let x and y be topological spaces. then X is said to be homotopic equivalent to Y, which is denoted by X is homotopic equivalent to Y if there is a continuous map, if there exists a continuous map F from the topological space X to Y, and a continuous map say G from topological space Y to X, such that when we compose G with F, we get the identity map on X, and when we compose F with G, we get identity map on Y. Sorry, this is not equal, this is homotopic. One can notice that this F is mapped from, this takes X to Y, so this is F, and then this G, we first move from X to Y, then come back via G, so G composite with F is a map from X to X, so that map has to be homotopic to the identity map on X. Similarly, when we first go from Y to X, that is we are operating G, and then come back from X to Y via the map F, then that map, that composite map, i.e. the composite map FOG, that has to be homotopic to the identity map on Y. In that case, these two maps, these two spaces X and Y are said to be homotopic equivalent. Now in next lecture we'll prove that, we'll give some examples of homotopic equivalent topological spaces, and we'll prove that this homotopy equivalence is actually an equivalence relation on the set of all topological spaces.